Welcome back, everybody. Today we are going to see some more linear algebra operations that we can do on vectors. We are going to see how we can actually fit a polynomial function to some x and y data using matrix operations. So what I'm going to do is create a pair of experimental data points. So this will be a vector that goes from 0 to 8. It's a column vector. And now this will be a y vector that I will see that it feels more or less a quadratic. So I am going to plot just to see how they look. S means for squares and K is color black, and I'm going to use marker face color to paint the squares black. Okay, so if we do this, it more or less has a quadratic function, so I'm going to change a little bit the last value to make it more quadratic. So this is more or less okay. So this is experimental data that we may want to fit. I'm going to go so that it looks more or less nicer. So we're going to try to fit this with a polynomial. So what is a polynomial function? It would be y equals a0 times a1 plus a1 times x plus a2 times x squared. So this is the generic definition of a second order polynomial. So how can we basically express this in a manner that we can take advantage of vectors? So for example, we could see that the first point would be a0 plus a1 times x1 plus a2 times x1 squared. If we do the same, well, actually we can express this as a vector product, where we would say y1 equals, and we will write this as a vector. So the first element would be 1 because the number that multiplies a0 is 1. Then we would have x1, then we would have x1 squared, and this would be multiplying a column vector. So this would be a0 a1 a2. So if you know dot products between vectors, you would see that 1 times a0 would give a0 plus a1 times x1 plus a2 times x1 squared. So we have re-expressed the polynomial expression for y1 as a vector product. So now we would take the second point, y2. So then we will notice that we have 1 x2 square, but then the vector that contains the coefficients of the polynomial is the same. So we could repeat this many times for all the data points. So basically, we can express this as a matrix operation, where yx, which is our vector, would be a matrix A times a vector called A, small a. So the small a vector would contain the elements a0, a1, and a2. So this is a typical matrix multiplication, matrix vector multiplication, that in Octave it can be solved, as in MATLAB also, using the backslash operator. So to find the vector A, we would do big A backslash yx. So we would solve the system of equations yx equals big A times small a by using this backslash operator. So in order to have this work, we have to define the matrix A, which we will by using, first we notice that we have as many ones as we have elements in y or elements in x. So basically we will write this ones size xexp. So this will give us a vector of ones with the same size as our experimental x1 and y values. Then we would get xx would be the second column, and the third column would be experimental x squared with the dot operator because this is element wise. So now we would obtain the A coefficients. So we are going to display them, and we use this disp function, and we are going to display my A coefficients are, and we are going to display the vector A, and we are going to transpose it because it will be a column vector, so we'll transpose it to display it in one line. So if we run this, we still get the same plot, and we can see, besides these error messages that I should get rid of, we see that the coefficients that we obtain are 0.163, 0.714, 0.096. So how do we know if that is correct? So what we are going to do now is create a theoretical set of data points. So we are going to do xcalc, and we are going to define more data points, because if we want to have a smooth plot, it's better to have many more data points than 8. So we are going to use the function linspace, which means make a linear space, make an equidistant set of points. Linspace takes in principle 3 arguments, which is the starting value, the final value, and the number of points. So our starting value, instead of typing it as a number, we are going to use the first value from xexp. Our final value will be xexp end, and our number of points, let's take 50. And this will give us a row vector, so we transpose it to make it column. So ycalc will be the first coefficient A, which would be a0, plus the second coefficient A times xcalc plus our third coefficient times x calc square. So this is again element-wise operations. So what we are going to do now is plot this and we are going to plot it as a red line. And let's see what happens. So indeed we see that we have basically found very easily a least squares fit of a polynomial function of order 2 to our data points. We can also verify, for example, that this equation gives the correct A. So how do we verify it? By doing this calculation again. So basically these are our modeled y values, and if we compare to yx, we see that our values are not the same, but they are close. And actually what we are plotting here are the interpolation of the y models over the 50 points that we used for the calculated x vector. So in here we have basically used linear algebra to solve this problem. But of course Octave has many functions that are built in that do a lot of the stuff that we would like to do faster and better. So there's a function called Polyfit, which is used for fitting polynomials. And Polyfit has many options, and the simplest option is this, that you give a x vector, a y vector, and a number of points. So we are going to do it here. So P equal Polyfit x y x, and the number of points, sorry, was not the number of points. The order of the polynomial that we're choosing is 2. So now let's display what Polyfit does. Let's display this. And also, well, let's display this first. So we see that here we obtain these values, which we call A0, A1, and A2. And Polyfit is actually returning the same values, but on the opposite order. So Polyfit first returns the largest coefficient, the coefficient of the largest order of the polynomial, then the second largest, and then the smallest. So the order is reversed from what we did. So we can check, for example, we'll call this ycalc2, and we would use P, but now we switch the third and first elements. So ycalc2 B. If this works fine, we see basically that we only see the blue lines. So basically both lines are on the same place. But in order to I'm going to slightly move one of the lines just to show that they are actually if we zoom enough, we will see that both lines are here, and I was not lying. So the polyfit function does basically what we did with this command and with this expression for this matrix, but of course it does many more things and returns a lot of statistical analysis of the fitting, the quality of the fitting. We could also calculate more things from this, but the purpose of this video was simply to show that you can very easily fit a polynomial to a function, to a set of experimental points. And for example, that could be very useful if you want to do some kind of automated baseline subtraction from spectra. You could select a number of points that occur on the baseline and fit that to a polynomial very easily and subtract it from your data. Generate a continuous set of values, or at least a vector that has the same number of data points as your experiment from the polynomial function that you calculated, and then subtract it from the experimental data. There are many uses for this kind of thing. So that is all for this video. I hope you found it useful. If you liked it, please like and subscribe.